Hi friend, welcome all to my educational channel Math A to Z. In this series of lecture, we discuss the series solution of second order ordinary differential equation. Before going to the series solution, it is essential to know some basic definition, like as what is a power series, when a power series is convergent or divergent, what do we mean by analytic function. Now we give the definition one by one. First, power series. A series of the form summation n equal to 0 to infinity an x to the power n, that is a0 plus a1x plus a2x square to infinity. This is a power series where a0, a1, a2, a0, a1, a2, these coefficients are constant. Also, the general power series can be written as summation n equal to 0 to infinity an x minus x0 whole to the power n. This is a0 plus a1 into x minus x0 plus a2 into x minus x0 whole square to infinity. This is the power series about x equal to x0, and this is the power series about x equal to 0, that is about the origin. Now, what is analytic function? A function f of x is said to be analytic at x equal to x0 if f dash x0 exists and f dash x exist on some neighborhood of x equal to x0. That is, if this x equal to x0 be the point, then f of x is derivable at x equal to x0, and it is also derivable in the neighborhood x0 minus delta to x0 plus delta, where delta be some arbitrary positive number, delta greater than 0. Here we consider a second order homogeneous linear ordinary differential equation as a0x into d2y by dx2 plus a1x into dy dx plus a2x into y is equal to 0, where a0x not equal to 0, and this is 1. And in canonical form, this equation can be written as this by dividing a0x both sides. Here this is 2 and p of x equal to a1x by a0x and q of x is equal to a2x by a0x. Here is also y. Now here we get two type of points. A point or any point x equal to x0. This is called ordinary point, or singular point. This is called ordinary point or singular point on the basis of p of x and q of x, the character of p of x and q of x. Now we first define the ordinary point. What is ordinary point? If P of x and Q of x both are analytic, at x equal to x0, then x equal to x0 is called ordinary point of ordinary differential equation 2. Now go to the singular point. What is singular point? If P of x, Q of x, either or both, any one or both, are not analytic at x equal to x0. Either or both are not analytic at x equal to x0. Then x equal to x0 is said to be singular point of 2. Right? Now, singular point are of two types. One, a regular singular point, and last, irregular singular point. Regular singular point and irregular singular point. Regular singular point. A point x equal to x0 is called regular singular point of the differential equation 2 if x minus x0 into p of x, we multiply x minus x0 with p of x, and x minus x0 whole square into q of x. If x minus x0 into p of x and x minus x0 whole square into q of x are singular, both analytic, then x equal to x0 is called a regular singular point. And what is irregular singular point? 2. Irregular singular point. A point x equal to x0 is called irregular singular point of 2 if either or both of x minus x0 into p of x and x minus x0 whole square into p of x are not analytic. Okay, so this is irregular singular point, regular singular point, and ordinary point. Now we go to 2 or 3 very short example to explain what is ordinary point, what is singular point, and what is regular singular point, and what is irregular singular point. Consider first d2y by dx2 plus x into dy dx plus x square plus 2 into y equal to 0. Clearly, from 1, p of x equal to x and q of x equal to x square plus 2. Here both p of x and q of x are polynomial of x. So we know that these two are analytic everywhere. So we say that any point any point x is ordinary point with respect to the equation 1. So any point be the ordinary point of the equation 1. Now we consider the second equation. Here p of x equal to minus 2x by 1 minus x square, because we first divide by 1 minus x square, and q of x equal to 2 by 1 minus x square, and this is minus 2x by 1 plus x into 1 minus x, and q of x is equal to 2 by 1 minus x into 1 plus x. Clearly x equal to 1 or x equal to minus 1, other than x equal to 1 or x equal to minus 1, p of x and q of x are analytic everywhere. So other than x equal to 1 and x equal to minus 1, all the points are ordinary point with respect to 2. But if we take x equal to 1, then p of x and q of x are both not analytic at x equal to 1. Now if we take x minus 1 into p of x and x minus 1 whole square into q of x, then we get minus 2x by 1 plus x. Here minus is plus, transfer to plus, and this is equal to x minus 1 into 2 by minus 1 plus x. So this and this both are analytic at x equal to 1. So we say that x equal to 1 with a regular singular point. X equal to 1 is singular, but it is regular. And similarly, x equal to minus 1 is also singular, but this is also a regular singular point. Now we go to another example. X square into x plus 1 whole square d2y by dx2 plus x square minus 1 dy dx plus 2y equal to 0. By normalizing this equation, we get p of x equal to x square minus 1 by x square into x plus 1 whole square, and q of x is equal to 2 by x square into x plus 1 whole square. Clearly x equal to 0 is singular point, because x equal to 0 is singular point because this and this both are not analytic at x equal to 0. Now if we take x into p of x, this is equal to x square minus 1 by x into x plus 1 whole square, and x square into q of x, this is 2 by x plus 1 whole square. Here this x square into q of x is analytic at x equal to 0, but x into p of x, this is not analytic at x equal to 0, because here in the denominator x present. So we say that x equal to 0 is singular and irregular. X equal to 0 be an irregular singular point. Now we check for the point x equal to, this is minus 1. Here x equal to minus 1 and x equal to minus 1 both are not analytic. So we say that x equal to minus 1 is singular. Now we take x plus 1 into p of x. This is x plus 1 into x plus 1 into x minus 1 by x square into x plus 1 whole square, and x plus 1 cancel. that is x minus 1 by x square, and x plus 1 whole square into q of x. This is 2 by x square. Clearly, both x plus 1 into q of x and x plus 1 whole square into q of x both are analytic at x equal to minus 1. So this is singular point. Also this singularity is regular singularities. So this is regular singular point and this is irregular singular point. In the last example, we have to check the singularities at x equal to infinity. So for checking the singularities at x equal to infinity, we change the independent variable x to 1 by t. Okay, and then in transform equation we check the singularities at t equal to 0. Right? Now we put x equal to 1 by t. Then obviously dx dt is equal to minus 1 by t square. Now dy dx, this is equal to dy dt into dt dx, and this dy dt into dt dx, that is minus t square. Now d2y by dx2, this is equal to d dx of minus t square dy dt, and this gives d dt of minus t square dy dt into dt dx, and this is minus 2t dy dt minus t square into d2y by dt2 into minus t square, and this gives the result t to the power 4 d2y by dt2 plus 2tq dy by dt, and putting dy dx d2y by dx2 in the given equation and put x equal to 1 by t, we get as 1 by t square d2y by dt2, that is t to the power 4 d2y by dt2 plus 2tq dy by dt plus 1 by t into dy dx, that is this minus t square into dy dt plus 1 by t square minus n square into y equal to 0. And calculating we get the result as d2y by dx2 plus 1 by t into dy dt plus 1 by t to the power 4 into 1 minus n square t square y. This is equal to 0. Here p of t equal to 1 by t, q of t equal to 1 by t to the power 4 into 1 minus n square t square. Now we test the singularities at t equal to 0. Clearly p into p of t, this is equal to 1, and t square into q of t, this is equal to 1 by t square into 1 minus n square t square. This p into p of t is constant, so it is analytic at t equal to 0, but here remains t square in the denominator, so this is not analytic at t equal to 0. So t equal to 0 is irregular singular point. So we say that x equal to infinity is also the irregular singular point of the original ordinary differential equation. Okay, this is the first class of the series solution of ordinary differential equation, and come back soon again with the second class. Thank you for watching.